Alright, in this video we're going to talk about molecular polarity and intermolecular forces. So we know that covalent bonds involve the sharing of electrons. But if the atoms that are sharing those electrons are different, oftentimes the electrons are not shared equally. And so the electronegativity is a measure of how strongly an atom attracts the shared electrons in a bond. And so the higher the electronegativity, the more that atom is going to attract the electrons. Now, in general, these have the same trend as ionization energies. As we go up and to the right in the periodic table, the electronegativities increase. Right? And we can see that based on the numerical values that we have here. Some of the atoms that are very electronegative that we're particularly interested in are nitrogen, oxygen, fluorine, and chlorine. We see these a lot in organic compounds, and they have high electronegativities, meaning they're attracting the electrons to them more than atoms like carbon and hydrogen. So when electrons are not shared equally in a bond, that bond is said to be polar. And in general, the electronegativity difference needs to be about 0.5 or greater, but there's some gray area in here, so don't get too hung up on that exact number. Again, remember, if I've got nitrogen, oxygen, fluorine, or chlorine, and they're bonded to a carbon, that bond is going to be polar. So electrons tend to spend more time around the electronegative atom. And because electrons are negative, if electrons spend more time around the electronegative atom, right, fluorine is much more electronegative than hydrogen, then that part of the molecule, or that atom specifically, gets a partial negative charge. And because the electrons are spending less time around the hydrogen, it ends up with a partial positive charge. So when we're looking at determining whether the molecule overall is polar, not just whether or not it has polar bonds, there are two things that we need to look at. One, are the bonds themselves polar? If it doesn't have polar bonds, then the molecule can't be polar. So when I have hydrogen and H2, that's going to be nonpolar, because obviously their electronegativity differences, or their electronegativities, are the same. Same thing with Cl2. With a molecule like CH4, I have different atoms, but because the electronegativity difference between carbon and hydrogen is only 0.4, right, that's less than the 0.5, right, I don't have any polar bonds, and so methane is going to be nonpolar. I think this is a really important thing to remember for organic chemistry. If anytime I have a molecule with just carbons and hydrogens, it's always going to be nonpolar because it can't have any polar bonds. However, even when I have cases where I have polar bonds, so oxygen is much more electronegative than carbon, so it's pulling on the electrons harder. If those electronegative atoms are arranged symmetrically around the central atom, as they are in the case of carbon dioxide, or as they are in the case of carbon tetrachloride, even though the bonds are polar, because those polar bonds all cancel each other out, that means the molecule overall is going to be nonpolar. So for a molecule to be polar, it's got to have polar bonds, and it has to be asymmetric, or the polar bonds can't cancel each other out. When that happens, then the overall molecule is going to be polar. So in the case of water, because it has this bent molecular geometry, the electrons are pulled towards the oxygens. It's not linear like in the case of CO2, and so we end up with a partial negative around the oxygen and partial positives on the hydrogens. So when we look at a molecule and we want to determine whether or not it's polar or nonpolar, I can't just look at the Lewis structures. I have to consider what the three-dimensional molecular geometry, or the three-dimensional shape is. Right? When I draw the Lewis structure of this molecule like this, it kind of looks like the chlorines are going to cancel each other out. But we have to remember this molecule with 4 electron groups on the carbon is tetrahedral. And so however I arrange these, I'm going to end up with 2 chlorines on the same side. And so the electrons are going to be pulled in that direction, and that molecule is going to be polar. Same thing here, right? I've drawn the Lewis structure so it kind of looks like it's symmetric, but this oxygen has 4 electron groups with toe-lone pairs, so it's going to be bent, and it's going to look something like that, right? So it's not symmetrical. The electrons are going to be pulled towards the oxygen, right? And the oxygen is going to be partially negative. The two CH3 groups are going to be partially positive. Now, this molecule, all of these carbons are trigonal planar, and so it is flat, like this Lewis structure depicts it. And so even though I have an electronegative bond between the carbon and the fluorine, because they're arranged symmetrically, right, this fluorine pulling electrons this way is going to be canceled by this fluorine pulling electrons that way. And so it's going to be nonpolar, right? So here's a similar molecule, still has two fluorines, but now the fluorines are not across from each other, right? And so they can't cancel each other out, and so that molecule is going to be polar. Now, one of the most important things that we're going to use, whether a molecule is polar or nonpolar, is to determine what the intermolecular forces are between molecules. And so whenever we talk about intermolecular forces, we're always talking about the force of attraction between two or more molecules, right? So I can't just look at one methane and talk about its intermolecular forces. When we're talking about intermolecular forces, we're talking about the attraction between two separate molecules, right? And so what is this attraction? This would be the intermolecular force. So there are just a couple types of intermolecular forces that we're interested in. The first one is called the dipole-dipole interaction. And so this intermolecular force occurs when both molecules are polar. Another way to say that is when a molecule is polar, it has a dipole moment, right? It has a negative end and a positive end. So acetone, CH3C with a double bond O, CH3, is polar, right? It's not symmetric. This carbon is trigonal planar, and I've got the CH3 and the CH3 and just the one O, nothing to cancel that out. So it ends up having a partial positive charge on one end, a partial negative charge on the other. And so when I bring it next to another acetone molecule, the negative end on one is attracted to the positive end on the other. And so this is a dipole-dipole interaction. Now, hydrogen bonding is another type of intermolecular force, and it's very similar to dipole-dipole interactions. Essentially, it's just an extra strong dipole-dipole interaction. So we know water is polar, it has a negative end and a positive end. And so the negative end of one molecule is attracted to the positive end of another molecule. But if I have a situation where one molecule is polar and it has a covalent bond between a hydrogen and an oxygen or and a nitrogen or a fluorine, that dipole-dipole interaction is so strong that we upgrade it to a hydrogen bond. So it's got to be polar. If I have a hydrogen directly covalently bonded to an oxygen, nitrogen, or fluorine, then we can have hydrogen bonding. Now, when we have mixtures of different molecules, it's important to note that the second molecule just has to be polar and have an oxygen, a nitrogen, or fluorine. It doesn't have to have a hydrogen connected to the oxygen, nitrogen, or fluorine. So that can be relevant when we start having mixtures. The third type of intermolecular force that we're interested in are called dispersion forces. I think our book might call this fleeting dipole-dipole interactions. Another common term you hear is London dispersion forces. And I apologize that there's so many different names for this, but you'll see all of these different names in different contexts, and so you have to know that these are all just the same thing. So dispersion forces result in fluctuations in the electron distribution within atoms or molecules. Right? And as an example here, I've essentially got a helium atom to try and demonstrate what these dispersion forces are. So, right, I've got my nucleus, I've got the electrons, they're flying around here, and if they're sort of evenly distributed, then there's not going to be any partial charges in that atom. But if we happen to find ourselves in a situation, just as the electrons are flying around, that both electrons are on the same side of the atom, because the electrons are essentially concentrated, that's going to give that side of the atom a partial negative charge. The other side of the atom that is electron deficient is going to have a partial positive charge. So this is kind of like a dipole moment, but it doesn't last, right? Because these electrons are not staying here, right? They're zipping all around. In fact, once they find themselves in this configuration and being next to each other, they don't like it, right? They're going to go away. And so these fleeting dipole moments only exist for tiny fractions of a second. But if I have this tiny instantaneous dipole moment in one atom, when I bring another atom next to it, it sees a positive charge that attracts the electrons, and so that causes what's called an induced dipole moment in a neighboring atom. And so that causes a brief, temporary, or instantaneous, or fleeting dipole-dipole interaction. But these are very weak, right? Because these aren't permanent like a polar molecule. They just exist for tiny fractions of a second, but they do provide for a force of attraction between all molecules, including nonpolar molecules. So if I have a nonpolar molecule, this is the only type of intermolecular forces that it has. But because all atoms and molecules have electrons that can, move around, all atoms and molecules experience these dispersion forces. Now, there are a couple things that determine how strong the dispersion forces are. So, polarizability is a measure of how easy it is for us to distort the electron cloud. A greater polarizability means it has stronger dispersion forces. This tends to increase with the size of the atom or the molecule, right? If the atom or molecule gets bigger, it has larger electron clouds, and in general, it's more polarizable. In fact, when we get to things like proteins that have hundreds of thousands of atoms, the dispersion forces can become quite strong because the electron clouds are so huge. Finally, the shape of the molecule can also influence the dispersion forces. More highly branched molecules are more compact and have weaker dispersion forces. So if we look at an example, if I wanted to compare this molecule, so 3 carbon atoms, this would be propane, and then I have 1, 2, 3, 4, 5, 6, this would be hexane. Because hexane is bigger than propane, it's going to have stronger dispersion forces, and that's going to lead to higher boiling points. When I compare these two molecules, they're essentially the same size, right? 1, 2, 3, 4, 5, 6, 7 carbon atoms, and 1, 2, 3, 4, 5, 6, 7 carbon atoms. And I'm not going to count the hydrogens, but if you want to, you can count those to see that that's the same as well. So the size is the same, but the shape is different, right? More highly branched molecules are more compact. And so if I imagine the electron clouds, right, I sort of have a spherical electron cloud and a spherical electron cloud, right? They only get to interact by a small amount. Whereas I have these long, sort of noodle-shaped guys, right, kind of like spaghetti, right? They get to interact a lot more. And so they're going to have stronger dispersion forces because their electron clouds can interact more with one another. And so this molecule will have a higher boiling point, or this compound will have a higher boiling point than this one. They're the same size, but the more compact molecules have weaker dispersion forces and are therefore going to have lower boiling points. So one thing to keep in mind, right? These bonding forces, like ionic bonds and covalent bonds, right? These are much stronger than the intermolecular forces, right? So hydrogen bonding is the strongest intermolecular force, right? But that's much weaker than covalent bonds and ionic bonds, right? These are the bonds that hold a molecule together. These are the forces that hold separate molecules together. Hydrogen bonding is the strongest, dipole-dipole is somewhat less, and dispersion forces are the weakest. So here's kind of a flow chart for determining what the intermolecular forces are when we're given a molecule. So the first thing you want to ask is it ionic or covalent? If it's ionic, then the intermolecular forces are ionic bonds. We don't deal much with ionic compounds in organic chemistry, at least not as much as we did in Chem 1211 and 1212. Most of the compounds that we're going to deal with are going to be covalent, although we will see some ionic reagents occasionally. So generally we're going to have covalent molecules, but it's good to ask this question. The next thing we want to know, is the molecule polar or nonpolar? If it's nonpolar, then immediately we know that the strongest intermolecular forces are dispersion forces. If it's polar, then it's either going to have dipole-dipole interactions or hydrogen bonding. If we have a hydrogen directly connected by a covalent bond to a nitrogen, oxygen, or fluorine, then we can upgrade that dipole-dipole to a hydrogen bond. If we don't have this scenario, then all it has is dipole-dipole interactions. So if we look at this example, I want to know the strongest intermolecular forces that would exist between two acetone molecules. And in this case, right, this carbon is going to be trigonal planar, so it's going to be bent. I have a polar carbon-oxygen bond, so this molecule is polar, and while it has hydrogens, the hydrogens aren't directly connected to the oxygen, and so it's polar, but I don't have a hydrogen directly connected to an oxygen, nitrogen, or fluorine, so we have dipole-dipole interactions. For this molecule, I only have carbons and hydrogens. And remember what I said earlier. If we only have carbons and hydrogens, those bonds aren't polar, and so the molecule can't be polar. And so if it's nonpolar, I immediately know we only have dispersion forces. All right, in this case, I have a polar bond. This molecule is, or this atom, central atom, is trigonal pyramidal, so it's not symmetric. So I have a polar molecule. So it's either dipole-dipole or hydrogen bonding. Now, because I have a hydrogen directly connected to an oxygen, nitrogen, or fluorine, I can upgrade that dipole-dipole interaction to hydrogen bonding.